All right, we're going to start to generalize what we learned before and to introduce so-called the surface integral. Remember, for a surface S, um, it is very, very important to have its parameterization. Okay, surface S, and the parameterization is supposed to be representing the collection of points on the surface. Okay, so the surface S is a collection of points. Okay, and for all those points, and we can have a so-called the position vector given by the parameterization we set up. If we use vector form, components form for the vector, then all the points coordinate will be given by those x, y, and z in terms of parameter u and v, and this d is the domain for the parameter to determine all the points on this surface S. So this is our starting point, because if you do not have the parameterization, you cannot really specify any part or any point on this particular surface. Okay, and another very important topic we should be really comfortable with is what is the so-called normal vector. On this surface S, giving parameterization, R of UV, and what we should know is indeed this cross product of the two partial derivatives for this vector valued parameterization R. Okay, and particularly the unit normal. The unit normal is important. Which is denoted by n, should be obtained by this regular normal divided by the length of this regular normal. And also, if we have, so for the surface that is given by the graph function r of rxy, and then you would know there's a little bit simpler formula. So let's just only talk about the general case, and we'll discuss this this surface given by the graph function a little bit later. Okay, so this is the unit normal. We got to be really careful. And then with this preparation, we can introduce the so-called the surface area, right? The surface area of this S for the portion which is determined by the parameter set uv from this D is given by the area formula of S, which is obtained by the integral. And this integral is the integral of the constant 1 over that particular portion of the surface, okay, which could be set it up after you know the parameterization. The parameterization is R, and also you have to specify the domain D for all the points on this surface. Okay, so if you could have that, then we got this calculation here. So our conclusion or big idea over here is the differential surface area is indeed the length of the regular normal vector times du dv. Okay, for u and v, that is in the domain that D to specify the portion of surface S. Okay, and obviously we can have 3 prime subpart for this surface area if the surface S is parameterized as the graph function as a graph of function z equals little f of xy, then we know the R, the parameterization is x, y, f of xy, and particularly the length of R sub x across R sub y is indeed given by this square root function explicitly. So the area for a particular surface, which is determined by the graph function, is still you're integrating constant 1 over that portion of a surface. But when you set it up, you can set it up this parameterization by using R of xy, and that is having a simpler form for you to calculate. Okay, so this is very, very important, and it'll help us to do a lot of a more complicated task. And this is our starting point for introducing so-called the surface integral. Okay, so for this surface area calculation, we already introduced the notation of differential surface area. So this integral is already called a surface integral, and that is this is a surface integral for constant 1. And we can generalize this idea to surface integral of scalar function g of xyz in 3-dimensional space as Okay, and the key here is to note the integrand is only evaluated on the surface S. So, which means if S is parameterized by R of UV, which means R of UV is equal to X UV, Y UV, and Z of UV, then this surface integral I is going to be G of X UV, Y UV, and Z of UV times ds, which means the UV is chosen to be from this domain D that is used to determine the portion of the surface. So G of X UV, Y of UV, Z of UV times the length of the normal vector times du dv. So this is what we actually calculate for the surface integral of a scalar function for this particular surface S that is determined within the domain D in the parameter plane. So this is a long description because there are many informations. There are many information you need to comprehend and know how to carry out the calculation. Okay, so you can think of this surface integral, the surface integral for a scalar function to be something like this. All right, so this is surface S is a surface, right? You can think of this as a surface that you have some sort of sugar coated on, and the sugar content is different at every point of the surface that is given by this function g of xyz. But this g of xyz may only just make sense and on that particular surface. So that is why that we have to restrict our evaluation of the g on the surface in this way by using the parameterization of the surface. So this is the logic behind, and we already discussed the calculation of surface area, which is sort of a special case of this. So we are not going to talk too much about it because our main focus here is to introduce a physical quantity we can compute by using mathematical formulation, especially this so-called the vector calculus, which is so-called the flux across a surface. Okay, the flux across the surface is supposed to be this. We have to explain flux. Well, maybe I should due to vector field F is given in this way. We have to explain all those notations, and there are two things. Well, this vector field F is relatively easy, and what does this mean? This is something that we have to understand and then explain. Okay, so here We can have some naive example you can imagine. So think about the airflow in or the air circulation near the surface of Earth, right? So when you watch the TV weather forecast on TV, and you always see there are big arrows, there are maps. Those arrows are indicating how fast the wind is blowing at a particular point in space above your city. All right, and then what you could imagine here, this F as is something as the wind speed at a particular point. Okay, and then you use dot product to dot the differential of the surface area, but with a direction. Okay, so if we dot this, then we can see we are actually projecting the vector field onto the normal direction of this surface area, and then we are just getting the pure flux that your vector field is penetrating through this surface. Okay, so let me explain a little better with this. So what is this? So we still remember, I guess, this, right? So the differential surface area is the length of the normal vector times du dv, and then this is the unit normal. Remember, the unit normal times differential surface area with n to be the unit normal. We can only write it down after we have the parameterization. And here, the S is supposed to be the differential surface area. As we said before, this has to be computed in this way, right? So now there's an interesting observation, I guess you already noticed. So we can write this as the regular normal vector divided by the length of a regular normal vector times the length of regular normal vector times du dv. So this is essentially becoming, so the surface area that is pointing to the normal direction at a particular point is indeed, we're canceling those two, it's indeed becoming just the regular normal vector times du dv. Okay, and from here we can see this is called the flux of the vector field across the surface S, flux across surface S due to the vector field F is that. So that has to be, so the flux across S due to vector field F is indeed oh, hold on for a second. Is this okay? We're actually computing this dot this one dot this this one, the normal vector times du dv. Okay, and then what you could do is convert everything into the parameter space uv. So this is becoming f. And then this vector field is dotted with the normal vector and then du dv. So now you can have a double integral. So this one is indeed a double integral for the UV variable in the plane. Okay, so this is so-called the flux. So this whole thing is the flux of the vector field F across the surface S, and in the end, we're converting it to a calculation for the double integral. So this is our logic for the calculation of surface integral for vector field F. Okay, so let me emphasize this one more time. So this is supposed to be the flux across the surface S due to this vector field F. And this is also the surface integral of vector field F on surface S. So the blue words are the mathematical description of what we need to compute, and the one in the blue circle is actually the physical description and people usually have in the physical and chemical or biological applications. Okay, I will have some example in next segment.